Welcome everyone. In this presentation, we're diving into one of the most surprisingly effective machine learning algorithms out there, the Naïve Bayes Classifier. Now, I know what you're thinking. Naïve, that doesn't sound like something I want making important decisions. But here's the twist. This naive approach often outperforms much fancier algorithms. It's like that friend who just guesses on exams and somehow gets an A. By the end of this presentation, you'll understand why this theorem powers everything from your spam filter to medical diagnosis systems. The English statistician, philosopher, and Presbyterian minister Thomas Bayes would be simultaneously confused and delighted, I think. Let's get started. So where do you actually encounter Naïve Bayes in real life? Spoiler, probably every single day. Spam detection. Every time Gmail correctly identifies that Nigerian prince email as spam, thank Naïve Bayes. It's been the backbone of spam filtering for decades. About 45% of all email globally is spam, and this little algorithm is your first line of defense. Medical diagnosis. Hospitals use Naïve Bayes for preliminary screening. When you want to catch every possible case of a rare disease, even if it means some false alarms, this algorithm shines. False positive? Annoying. Missing a real case? Potentially catastrophic. Sentiment analysis. Companies monitor social media to see if people love or hate their products. Naïve Bayes reads those tweets and categorizes them faster than any human could. Fraud detection. Your credit card company runs every transaction through classifiers like this. Is this purchase pattern normal for you, or did someone steal your card to buy 47 gaming chairs in Bulgaria? The common thread? All of these involve categorizing things based on multiple features. Exactly what Naïve Bayes was born to do. Let's cut through the math intimidation and get to the heart of what Bayes classification actually does. It's surprisingly simple. Imagine you're a new record, maybe a customer, a patient, or an employee, and you want to know what's going to happen to you. The Bayesian approach is basically, let me find everyone in my historical data who looks exactly like you and see what happened to them. Think of it like moving to a new city. Want to know if you'll enjoy the nightlife? Find people who have your exact same job, income bracket, age, and number of cats. If 78% of them go out every weekend, well, you probably will too. In our example here, we have a 35-year-old urban professional who shops online. We search our training data, find 100 similar people, and discover that 78% of them stayed with the company while 22% left. So our prediction? This person is likely to stay. Simple, right? But here's where it gets tricky and where the naive part comes in. We'll get to that in a moment, because this elegant approach has a fatal flaw when dealing with real-world data. Before we go deeper, let's dust off a concept from Statistics 101, conditional probability. Don't worry, I promise to make this painless. Conditional probability is simply probability with context. It's written as P open bracket, A vertical bar, B closed bracket, which reads as the probability of A given that B has already happened. Here's a relatable example. What's the probability of getting wet today? Depends on a lot of things, right? Maybe 15% on an average day. But what's the probability of getting wet given that you forgot your umbrella and it's raining? Suddenly, that probability shoots up dramatically. Context matters. In our classification world, we're asking, what's the probability this record belongs to class X, given that it has these specific features? That's the question at the heart of Bayesian classification. If someone has low income, poor credit score, and high debt, what's the probability they'll default on a loan? That conditional probability is exactly what banks want to know before handing over money. The key insight, the vertical bar, means given that. Everything after the bar is your context, what you already know to be true. Let's make this concrete with an example that gives HR departments everywhere sleepless nights. Employee turnover. Picture this. A tech company is hemorrhaging talent. Every time a skilled employee walks out the door, they lose institutional knowledge and face recruiting costs between 50% and 200% of that person's salary. That's potentially $150,000 to replace a $75,000 employee. Ouch. The VP of HR has a brilliant idea. Instead of reacting after employees resign, usually with that awkward 2-week notice and an already signed offer letter from a competitor, what if we could identify flight risks early? They dig through the data and notice something interesting. They've been tracking whether employees received promotions in the past 2 years. Someone wonders, could being passed over for promotion predict who's likely to leave? Makes sense, right? Few things breed resentment like watching colleagues get promoted while you're stuck in place. Looking at our training data of 1,000 employees, we can calculate, among employees who weren't promoted, about 6.5% left. But among those who were promoted, a surprising 21.7% still left. Wait, what? We'll dig into this more, but the pattern emerges. Promotion status gives us information about departure risk. This is conditional probability in action. Probability of departed given the promotion status gives us different numbers depending on the context. Here's where the exact Bayesian classifier runs headfirst into a brick wall. Remember, the whole approach depends on finding training records that are exactly like the new record. Every single predictor value must match perfectly. With one predictor, like our promotion example, this was easy, but real-world problems rarely stay that simple. Let's say you're trying to predict how a voter will vote, and you've got 8 demographic variables: gender, ethnicity, income bracket, region, voting history in the last 2 elections, family composition, and marital status. That's just 8 variables, modest by data science standards. Yet, even with a large sample, you might not find a single person in your training data who matches all 8 criteria perfectly. Your exact Bayesian classifier just shrugs and says, "I've got nothing for you." The math here is absolutely brutal. Every time you add a new categorical variable with, say, 5 equally common categories, you reduce the probability of finding a match by a factor of 5. Add a few more variables and you're essentially guaranteeing that most records will be orphans with no identical twins in the training set. It's like trying to find your exact doppelganger down to the freckle. Mathematically possible, practically impossible. This is the exact Bayes procedure's fatal flaw. Theoretically elegant, but practically useless for anything beyond toy problems with 1 or 2 predictors. Enter Naïve Bayes, the pragmatic cousin who's willing to make some simplifying assumptions to actually get things done. The key insight? Stop insisting on exact matches. Instead of limiting probability calculations to the tiny or non-existent set of records that match perfectly, Naïve Bayes uses the entire training dataset. Here's the magic trick. We assume that all the predictor variables are independent of each other within each class. This means instead of asking, what's the probability of seeing this exact combination of features, we ask, what's the probability of each feature separately, and then multiply them together. Now, is this assumption actually true? Almost never. In real life, features are correlated all the time. If someone got a poor performance review, they probably also got passed over for promotion. These things don't happen independently. But here's the surprising part. It works anyway. Why? Because most classification tasks don't need probabilities that are accurate in absolute terms. What they need is a reasonably accurate rank ordering. If employee A is riskier than employee B, the model needs to reflect that ordering, even if the exact probability numbers are a bit off. Think of it like a GPS that always gets you to the right destination but occasionally quotes the wrong travel time. Still useful. The destination matters more than the ETA, the expected time of arrival. This willingness to sacrifice mathematical purity for practical results is why it's called naive. It's not stupid. It's just willing to make simplifying assumptions that turn out to work remarkably well. Don't let the formula scare you. It looks intimidating, but it's actually quite elegant once you break it down. Here's what we're computing. The probability that a record belongs to a certain class, given its features. Step 1. Start with the prior probability. How common is this class in general? If 18% of all flights are delayed, that's our starting point for the delayed class. Step 2. For each feature the record has, ask, how common is this feature among records in this class? Then multiply all those probabilities together. This is where the independence assumption kicks in. We're assuming we can just multiply them without worrying about correlations. Step 3. Do the same calculation for every possible class. Then normalize everything so the probabilities add up to 1. Whoever has the highest number wins. The beauty is that you can often skip the normalization step entirely. Since the denominator is the same for all classes, you can just compare the numerators. Whoever's bigger wins, less math, same results. One thing to note, those probability values Naïve Bayes produces, while correctly ordered, aren't calibrated the way you might expect. A 30% departure risk from Naïve Bayes isn't the same as a true 30% probability. The rankings are trustworthy, the absolute numbers, not so much. Keep that in mind when interpreting results. Let's work through a real example using flight delay data. This is exactly the kind of problem where Naïve Bayes shines. We have over 10,000 flights from January 2025 with 5 predictors, day of week, scheduled departure time binned into hourly slots, origin airport, destination airport, and carrier. The outcome is binary, delayed more than 15 minutes or on time. Now, here's the challenge. If you want to classify a specific flight, say a Delta flight from Boston to San Francisco, departing between 10 and 11 a.m. on a Sunday, you might not find any flights in your training data with that exact combination. 5 predictors with multiple categories each. The combinations explode. With exact Bayes, you'd be stuck. But with Naïve Bayes, we just break it down. What proportion of delayed flights were Delta flights? What proportion of delayed flights departed on Sundays? What proportion departed in the 10 a.m. hour? And so on. Multiply these together, do the same for the on-time class, normalize, and boom! We get probability of delay to be approximately equal to 20.5% and P of on-time to be approximately equal to 79.5%. The flight is more likely to be on time, so that's our prediction. And here's the magic. We made this prediction without requiring any exact matches in the training data. That's the power of the independence assumption. Mathematically questionable, practically invaluable. Here's where things get interesting and a little humbling. Our Naïve Bayes classifier achieved 82% accuracy on the flight delay data. Sounds pretty good, right? Well, here's the awkward truth. If you just predicted on time for every single flight, you'd also get 82% accuracy. Because 82% of flights in the dataset were on time, by a simple accuracy measure, the Naïve Bayes model does no better than the naive rule of just guess the majority class for everything. But wait, don't throw out the algorithm yet. Accuracy is a terrible metric when you're dealing with imbalanced classes, which is almost always the case in interesting real-world problems. Fraud is rare, diseases are rare, flight delays are relatively rare. What Naïve Bayes does excel at is ranking. Look at a lift chart and you'll see the model does a great job of putting the highest risk cases at the top of the list. If you only have resources to investigate 20% of transactions for fraud, Naïve Bayes will help you pick the right 20%. This is the key insight. When your goal is catching rare events, ranking matters more than raw accuracy. A hospital screening for a rare disease doesn't care if the model gets 99% accuracy. They care if the model flags the actual sick patients, even if it means some false alarms. Here's a powerful twist on the standard classification approach. Instead of just assigning records to whichever class is most probable, you can set a cutoff threshold. Think of it like installing an adjustable sensitivity dial on your classifier. In our employee turnover example, HR doesn't want to win an accuracy contest. They want to catch flight risks. So instead of classifying everyone based on the most probable class, which would put almost everyone in will stay, they say, flag anyone with greater than 20% departure probability for proactive outreach. Sure, some loyal employees will get flagged. Awkward conversation. You say to the employee, "We noticed you might be unhappy." And the employee responds, "I literally just bought a house nearby." But that's a trade-off HR is willing to make if it means catching the employees who are genuinely eyeing the exit. For disease screening, the cutoff might be even lower, maybe 5%. A hospital would rather run extra tests on 100 people who turn out to be fine than miss the 5 people who actually have the disease. The key insight: the cutoff is a tunable parameter. You can slide it around to balance false positives against false negatives based on your specific costs. Missing a fraud case might cost $10,000. Investigating a legitimate transaction costs $10. So you'd set a very low cutoff. This flexibility is one of Naïve Bayes' superpowers. You're not stuck with binary predictions. Let's talk about why Naïve Bayes has earned its place in every data scientist's toolkit. Speed. This thing is fast. While deep learning models take hours to train, Naïve Bayes trains in milliseconds. It's just counting and dividing, basic arithmetic. Need to retrain your spam filter every hour as new patterns emerge? No problem. Simplicity. There are essentially no hyperparameters to tune. You don't need a PhD to implement it. Compare that to neural networks, where you're agonizing over learning rates, dropout percentages, and architecture decisions. Ranking power. As we discussed, Naïve Bayes excels at putting high-risk cases at the top of the list. When you're doing fraud detection or medical screening, this is exactly what you need. Scalability. As you add more predictors, naive Bayes handles it gracefully. This is where it has a huge advantage over exact Bayesian methods, which collapse under the weight of even a handful of features. Here's the remarkable part. Naive Bayes often outperforms fancier, more sophisticated classifiers, even when the independence assumption is clearly violated. It's like the scrappy underdog that keeps winning despite breaking all the rules. When you're prototyping, always start with naive Bayes. It gives you a solid baseline, runs instantly, and might just be good enough that you don't need anything fancier. Now for the fine print. Every algorithm has its kryptonite, and naive Bayes is no exception. Limitation 1. Data hungry. Naive Bayes requires a large number of records to deliver good results. With a small training set, the probability estimates become unreliable. It's like trying to understand a city's culture after talking to just 3 people. You might get lucky, but you're probably missing the full picture. Limitation 2. The zero probability problem. This is the nasty one. If a particular predictor category never appears in the training data, naive Bayes assumes any record with that category has zero probability of belonging to any class. Here's a scary example. You're building a model to predict who will buy premium tech support, and one of your predictors is experienced major data breach. If your training data happens to contain no customers who experienced a breach, lucky them. Naive Bayes assigns zero probability to the outcome for any new customer who has experienced a breach. But wait, those are exactly the customers who'd want premium support. The zero outvotes all other evidence. The solution? Laplace smoothing. In scikit, just set alpha to be greater than 0 in multinomial NB. This replaces zero probabilities with small non-zero values. Problem mostly solved. Limitation 3. Uncalibrated probabilities. The rankings are trustworthy, the absolute numbers, not so much. This is why you rarely see naive Bayes in credit scoring, where lenders need calibrated probabilities for precise risk-based decisions. Let's wrap up with the key points to remember. 1. The independence assumption is technically wrong, but it works anyway. This is one of those beautiful cases where a simplifying assumption that shouldn't work somehow does. Don't question it too hard, just enjoy the results. 2. Naive Bayes shines at ranking, especially for rare events. When you're looking for needles in haystacks, fraud, disease, employee flight risks, this algorithm will put the most suspicious cases at the top of your list. 3. The cutoff method is your friend. Don't settle for binary predictions. Adjust the threshold based on your specific costs of false positives versus false negatives. 4. Always use Laplace smoothing. It's enabled by default in scikit, but make sure you don't accidentally turn it off. Zero probabilities are classification killers. 5. Start with naive Bayes. It's fast, simple, and often good enough. If it works well enough for your use case, you're done. No need to spend weeks tuning a neural network. And remember, naive Bayes is naive, not stupid. Thomas Bayes inadvertently created something that powers billions of decisions every day, from your spam filter to medical diagnosis systems. Thanks for your attention.